Okay. So every once in a while, you guys at home, I may turn away for a moment to address somebody in the class here. When I turn back, I'll try and repeat. If there was a question, I'll try and repeat it so you guys get to hear it as well, and you can hear my answer if I have to repeat it. And if I forget to do that, remind me of it because it's easy to get distracted as I'm talking to people here in the classroom. Okay, so we're on and recording. If you guys would download the exercises for tonight. It's in the class session 7, I believe it is, for under the tab lab for sections 003 and 004. You guys, if you like Ali's lectures better, you can go. I think by next week will be set up pretty regularly broadcasting as well, and you can switch back and forth, or you can, you guys from that side can come over here, or certainly afterwards you can listen to both of the lectures online, stream them online, just to see what the other group has seen or been working with. Ali tends a little bit more technically detailed than I am, and he tends to use SPSS a bit more than I do, especially at least for the lab exercises. So you get a different perspective. It always helps to see the material more than one time, and especially to get a different perspective. So if you've had a chance to download this exercise, I'm going to blow it up a little bit so we can read it a little bit better here. Okay, so I tried to go with a theme today. And you'll get the theme in a second. Suppose we want to know the true population proportion, P, of Irish Americans who approve of a wider representation of all groups in the St. Patrick's Day parade. In 2000, the parade committee asked a random sample of Irish American parade participants if they approved of a wider representation of all groups. Out of 1,381 respondents, 496 said that they approved. Okay, so that's a sample, correct? That's not the entire population of everybody that took part in the parade. That would be easily hundreds of thousands of people, most likely. Did anybody go to the parade today? Yeah. Yeah. Did you really? Yeah. No kidding. Well, how was it? A little cold though, right? Yeah. Okay. All right. Are they enforcing the no drinking rules and stuff like that? Yeah. Yes, I guess, yeah, yeah. They're as you guys, you may not be old enough, but there were a few incidences, and actually, to tell you the truth, the worst one was not at the St. Patrick's Day parade, but there were a few problems that arose from a lot of drinking and stuff like that at some of the parades, and it's been about 15 years now where at most of them they enforce a no drinking policy when you're on the sidelines of the parades. Of course, they used to enforce it a bit more, but they've loosened up a bit now that they haven't had really big problems for a while. So at any rate, what proportion of the sample approves? We don't know what proportion of the population approves. If we knew this, we wouldn't. In order to know that, we'd have to ask everybody that took part in the parade. Okay. On the other hand, we can find out what proportion of the sample approves. What's the first rule here? What's the first assumption that we make about this sample? Anybody want to guess here? Well, yeah, that it's normally distributed. If we took samples over and over again, half of them would be above the real population, real proportion, half of below, and so on and so forth. What even more important than that? If you do a survey, if you ask people about their opinions about things, what's the single most important thing that you're concerned about? That your sample is random, right? So if you only sampled old white-haired Irishmen, right, then you might get a different look at what the entire population would be than if you only sampled people that were under 25, right? So it's important that the sample be random if we really want to know what the entire population is. Okay, and so in order to do that, now I'm getting some white hair also, so I can talk about those guys that way, right? So at any rate, except I'm still a hippie, I think. I'm not, I think a little younger, I hope. At any rate, so let's take a look at this proportion. So the proportion, I'm going to pull up Excel because it'll be easier to work with. I'm going to open Excel spreadsheet, start a new one. I'm going to make it a little bit bigger so we can read it again. I got a little bit of a frog in my throat today, so excuse me. Okay, so 496 out of 1381. So 496 out of 1381. So the proportion I'm looking at, what will I call that proportion? Is that proportion P? P is usually what I designate as the population proportion. So to distinguish it from the population proportion, I'm going to call it P cap. And I'm calling it P cap because I can't easily draw a little cap over the letter P right now. So I'm going to call it P cap, and that proportion is going to be 496 divided by 1381. So we predict that roughly 36% of the people that took part in the parade favored a wider participation. That was in 2000. Okay, so now if I want to predict the population proportion, I'm not that interested in what that sample is. I'm really interested in what the population proportion is. I want to know how precise this sample is, how precisely I've predicted the population. So I would rather have a range that I understand what my likelihood of being wrong or being right is than just having a single number that I have no idea how accurate I might be. So as a consequence, we often decide that we want to have a confidence interval for a proportion like this. Okay, so let's create a confidence interval for this. Okay, so now most of the time you're interested in a 95% confidence interval, right? We want to narrow our chances of missing the true population proportion down to what percentage of error are we talking about? If it's a 95% confidence, 5%, right? You got a 5% chance of being wrong, missing the true population proportion. 5% chance of being wrong in our prediction that it's between these two numbers. What's the name of that type of error? Right? Just talked about it before. There's two kinds, alpha and beta, right? So that would be an alpha error. And you refer to the percentage, the likelihood of being wrong, if you say this is my confidence interval, as the alpha error. So our alpha error, our alpha equals 0.05, 0.05. Okay, our chance of being wrong is going to be 5%. Okay, so I'm going to go ahead and calculate that. Well, first of all, the first thing I need to calculate is P cap. I got that. Next thing I need to calculate is my standard error. Okay, how do I calculate my standard error for a proportion? Okay, I'm going to write it here. P times
1 minus P.
I'm going to use Q. A lot of times you'll see in the formulas in the books they'll use Q to represent 1 minus P because they can save a little writing over N. Right? Over N is right? Okay. And that's the whole thing's over square root. So we're going to find square root of the whole thing. So that's going to be equal to the square root, parentheses, of what is P? P is 0.359. Right? 359. I'm not going to bother. I'm going to call it 0.36. I'm going to make things simple for myself. Times 1 minus P, which is going to be 0.64. Everybody with me so far? Divided by the sample size, which was 1381. Okay, tell me something about that sample size. Beyond the assumptions that we are normally distributed and that we have a random sample, a non-biased random sample, okay, what's the third assumption we make about this in terms of sample size? Anybody remember that from any of the readings? We're gonna work on the confidence interval, but there's another rule about doing this. What if I told you that I took a sample of 10 people and I only got 3 of them got 3 that were in favor of this, and I was going to find a confidence interval? Would that meet my assumptions for the confidence interval for my hypotheses? It wouldn't, because I need a sample size of at least 15 on each side of this possible outcome. Otherwise, I can't really depend on my standard error. It's not accurate enough for me to have any sort of confidence in it. So somewhere buried in the textbook or the readings or the PowerPoints, you'll see a little thing in there about proportions where it says that you have to have a sample size of at least 30 if it's 15 and 15. But the important thing is you have 15 in each group. So in one group we have 496, in the other group we have 1381 minus 496, or about 880 or something like that, right? Everybody got that? Got to have at least 15 in each group. Okay, so we have that, so I'm just going to go ahead. My standard error is 0.0129. Okay, so now I'm going to calculate my confidence interval. My confidence interval is going to be equal to the mean, right? Plus, I'm going to go plus first, plus, now what am I going to use for a 95% confidence interval? 1.96. Okay, very large sample size. I'm going to use 1.96, just like this, just the z-score, times my standard error, and I'm just going to click in here to copy it. Okay, and that becomes, oops, I did something. Oh, you know what it is? I didn't multiply there. Well, let me escape that. I know what I did wrong. Please leave me alone. Times. Okay, and it's, nope, something wrong there. No, it's right, right? And I'm going to do it again, equals 1.96 times my standard error. Okay, and I'm going to subtract that from the mean, which is 0.359 minus that quantity is going to be about 0.33. So my confidence interval is, I'm going to round at this. You really shouldn't round until the very last step, right? So because if you can imagine, if I rounded the standard error, for instance, then I multiplied by 1.96, I've doubled my error, right? I might have gotten, instead of rounding down at the next step, I might have been able to round up because the number would have been different. So you normally would only round at the very end. I'm doing it just to expedite this whole thing. 3.384, and this is equal, oops, 0.384 and 0.334. Okay, so we're 95% certain that the true proportion of people participating in the parade in 2000 is between 33 and 38%. Okay, so anybody want to hazard a guess as to what the number that we're subtracting and adding to the to our mean is? In other words, the value, let's see, equals 1.96 times the standard error. What is that value called? It's plus or minus what I think the real value is. Yeah, bingo, margin of error. In fact, in polls, in political polls, that's one of the places where you wind up with margin of error. And very often, political polls are proportions. What proportion of the vote is this guy getting? What proportion of the vote is this guy getting? So they're doing exactly this kind of calculation, and they're comparing the different candidates. You'll notice that in political polls, that very frequently they will give you a percentage for this candidate and say that, oh, we think he's got 32% of the vote. And this other guy has got 37% of the vote, and so on and so forth. And then I'll say the margin of error is 3%. But they won't distinguish between the guy who's got 12% and the guy who's got 37%. Anybody, wouldn't you expect the margin of error to be different since they're calculating their standard error based on that guy's proportion of the vote? You would think it would be different, right? They do something a little bit tricky there. What they do is when they calculate the standard error, they use P, they use exactly the same thing, P times 1 minus P, divided by N. Okay, I'm not going to put the parentheses in there, and then they take the square root of it. They do exactly the same thing that you would do with everything else, except when they put in P and 1 minus P, they don't put in the P or 1 minus P for that individual candidate. For all of the candidates, they put in 0.5 and 0.5 for P and 1 minus P. Anybody have any idea why 0.5 and 0.5 might be a good thing to put in there? Exactly right. If you had somebody that had 40% of the vote, it'd be 0.4 times 0.6. If you had 30% of the vote, it'd be 0.3 times 0.7, so 0.21. The biggest number you can get for the error is 0.5 times 0.5. So they use that for calculating the standard error for all of the candidates and for the margin of error for all of them. So they don't have to report this guy as being plus or minus 2%, and this guy is plus or minus 3.2%, and this guy 5%, and so on and so forth. They can just report a single margin of error. Okay.
They do that for reporting, but did they do that for the actual elections when they decided they need to do a recount?
No, they don't do it. We're in the United States. We don't do recounts based on proportions. We do it on actual votes. So I can't think of a single six. That it's interesting. You should bring that up. But one of the big issues when they were talking about Chads in the election in the I guess it was 2000 election or 2004. It was 2000 election when they were talking about Chads. They were presumably elderly people in certain counties were disproportionately affected by confusing elements in the ballot. And you could almost predict which ones were wrong because, like 99% of the people that voted this way, for this candidate would almost always vote for this amendment or something like that. So there was speculation about whether it would be permissible to correct the error, the chads that the ballots that were in error by using a pattern on the other votes and so on and so forth proportionally, right? And of course that's illegal. It has to be an actual count. It can't be anything but an actual count. Okay. Same thing with the census. The census, for instance, in New York, we know that in this neighborhood in New York, that Hispanics are significantly undercounted in this area because some of them, if they have like immigration issues or they may not have papers and so on and so forth, they will avoid the census. And we know that. And you could actually do a really rigorous survey of a random selection of blocks in this neighborhood and figure out that they're undercounted by 30%. The problem is that the census is actually in the Constitution that it has to be a physical count. So you can't make a correction in the census, even though you know it's wrong and have a rough idea or you have a good idea by what proportion it's wrong, unless you actually have a constitutional amendment, which then we haven't had one for a long time. I mean, 92. It's given the climate, you can imagine, given the political climate these days, you can imagine how difficult it would be to manage to get an amendment on the Constitution accepted. So at any rate, that's one of the things they do there. So I'm going to move on to the next part of this. And you can answer these questions for yourselves. Suppose this study is repeated in 2014, and this time we get 400. It's a smaller survey. We got 403 people out of 802 participants that approved this. Okay, so this time it's 402 out of how many did I say? 403 out of 802. Okay, and I'm going to give you guys a chance to do this one as well. Why don't you guys get ahead of me for a minute or two and calculate the p-cap, the standard error, and the confidence interval. Same assumptions, right? No problem with the assumptions here. And the sample size is large enough. That's a random sample. We expect it to be normally distributed. Or we repeated samples to be normally distributed. Let's try this. Oh, wow. Oh, actually, let me see if anybody's complaining. Can you repeat the comments? Yeah, I have a few complaints. I'm sorry. As a matter of fact, I'm trying to get mic'd up right now, and for you guys online. Wait. Let me talk first. And this should help out quite a bit. So I'm going to check what you guys see if you can hear me in a second. Let's do it. Okay, now we got to go in here and select mic, sound. It doesn't see it yet. Is it turned on?
No. Can you tip it?
No, it should. Let's see, output, input. It should see it. When you plug it in, it should see it. it's not seeing it. Does it use a battery or anything like that, or
It
just?
does, and I put a battery in it. So I'm 100% sure this thing actually works, but
It should pop up on here. Parade came to you, eh, Danielle? I guess you live on First Avenue or on Fifth Avenue. Yep.
plus, that's right, plus.
Yeah.
It's on. Yeah, I don't know if it's not on now. I have to return it. You just bought it.
Tell you what, hang on to it, but before
Okay.
you return it, let's give it a try later on.
Okay.
Okay, guys, I'm back. That didn't work out. I'll try and repeat the questions, or at least come back and turn back again and repeat what I'm saying, if I can. We tried a mic, but we didn't have any luck with it. Okay, so let's move on to this problem. Okay, so I'm gonna run through this problem. P cap for me is going to be equal to 403 divided by 802. Okay, is about 50%. My standard error is going to be equal to, it's going to be equal to 0.5. I'm going to call that point. I'm going to simplify this 0.50 times 0.50 over the sample size, which is 802. I'm going to find the square root of that. And I'm going to hit enter, hoping I did this right. And there we go. That's my standard error. And my confidence interval is going to be, it's going to be equal to, I'll do minus this time first, P cap minus 1.96, right, times my standard error. And that's equal to about 47%. And P cap, oops, P cap, oops, equals P cap plus 1.96 times my standard error. Oops, did I forget something there? Okay, good. All right, so I get a range of, for my population proportion, I am 95% certain that the true population proportion is going to be between 46 and 50, 47 and 53% of that population from 2000 and whenever it is, 2010. Now, when I did it for 2000, I got 33 to 38%. So I'm 95% sure that this group, that this population was between these two numbers, and I'm 95% sure that this group was between these two numbers. That gives me some level of confidence that there is a difference between these two groups. In reality, the confidence interval really just tells you, predicts a range within which you expect the true proportion or the true mean of the population to fall. We're going to wind up using these kinds of spreads, differences in variability and differences between the means to kind of make hypotheses that try and hypothesize whether or not this population is different from this population. And we're going to be using things like this to actually figure out whether there's a real difference between these two groups or whether the difference is just due to chance. Well, if they were closer together, or perhaps if they even overlapped, we'd be a lot more suspicious about if there really was a difference here than if they were this far apart. Okay, so we're actually going to put that to work soon. Okay, but just on 1C, I'm going to just take propose looking at a third study, okay, non-participants to the parade. We only sampled 56 people. Out of the 56 people, 46 approved of opening up the parade to a wider range of groups. Can I go ahead and do this, find this proportion for those 46 out of 56? Is there a problem with that particular survey if I want to work with proportions. Okay, you guys online too. And how about you guys back here? Got an opinion? Problem there? Can I go ahead and find the, P is 46 out of 56. My standard error would be whatever that is, 0.8 times 0.2. Problem there? You guys have very short memories. What did I say about sample size? It's got to be 15 in each group too, right? Not just 30, but 15 in each group. One group has 46. What's the other group got? 50. Yeah, it's only got 10 people in it. I can't trust my standard error in this situation. Okay, it won't fit my assumptions. All three of my, it won't fit that third assumption about how we're going to handle this. Right, too small sample size in that one group. Exactly. Because imagine this. You might take a sample of size 30 or something like that, but then if the proportion of people in that population that satisfy one part of that is very small, like 1 out of 100, you may or may not be able. You might not find anybody in that sample that satisfies that criteria. Right. So, I mean, if the sample is too small, you can't depend on it. It's got to be at least 15 in each group. That magic number 30 is going to come up in a little while again. Okay, let's take a look at this next example. This one deals with means. You randomly sample 40 New York City pubs on St. Patrick's Day. See the theme here? Okay, and find that they inventory an average of 42 types of beer. That wouldn't be that unusual, right? Most pubs now carry a lot of different beers. You calculate the standard deviations for these pubs from your study data and find that it is 6.3 beers. Okay, now I'm looking at this and I'm saying to myself, I have a problem here. My formula, when I work with a formula for calculating for finding the standard error, right? I usually use the population standard deviation, sigma, but I don't know that here. I calculated my standard deviation from that sample of 40 pubs. Now the mean of that sample approximates the population mean. The standard deviation of that sample approximates the standard deviation of the population. The problem is that we're using the standard deviation at sigma. We're using that to understand how variable the data is. So it's important we have the population standard deviation so we have a better handle on how variable the data is. If we wind up using a standard deviation calculated from the sample, even though it may be a pretty good approximation, what have we just introduced? We just introduced more error that wasn't part of the original deal. The original deal was that we just use sigma over the square root of n, and that would give us a really good handle on the variability of the population or of the repeated samples. Right now, in this case, we've added this extra level of possible error. So we have to make up for that. So if I'm calculating a confidence interval and I want to accommodate for I want to remove more chance of being wrong, accommodate a bigger source of error. Do I make that confidence interval narrower or wider? Wider. How do you guys online feel? Wider or narrower? I want to make it wider, right? Because making it wider makes up for that extra error that I'm introducing. Okay, we're going to discuss now how we add that extra margin. Okay, so when a sample size of 40 is not so bad, that's not really that small a sample when we're talking about a numerical variable. So first of all, 40, of course, is going to be X bar. It's going to be our sample mean. It's not going to be our population mean because we're trying to get a handle on that. 6.3 is not sigma. It's the standard deviation of the population. Calculate standard error for repeated samples from this population. Okay, well, standard error is going to be, for size 40 is going to be sigma, or in this case, it's going to be the standard deviation over the square root of n. Okay, except that we know that's not going to be as accurate as knowing sigma. Calculate a 95% confidence interval for the beer inventory mean based on this sample. So I'm going to get my Excel spreadsheet out. And you can do this with a calculator if you want. I'm just using Excel because I'm comfortable with it and I can do it fairly quickly. 40 is the number of beer. 42. 42 is the number of beers. right? Okay, and that's X bar, right? It's not mu because it's the sample mean, not the population mean. So it's not mu, it's X bar. Okay, we got that by sampling 40 New York City pubs. We did them randomly. We didn't go on a pub crawl. We actually went on a map first and like randomized them and stuff like that, and sent unbiased people out there to count. Let's say, yeah, you guys. What have you guys? Isn't there a movie with zombies in it and stuff like that?
Shaun of the Dead?
Right, exactly. Was it Shaun of the Dead? World's End. That's it. It's the same guy, right? Right. So that's not World's End that we're looking for here, right? We just went in a phone book and randomly selected these guys. Okay. So at any rate, now 42 is our mean X bar for our sample. 42 different kinds of beer. My standard deviation is again 6.3. My standard error is going to be equal to, the only thing I got here is my standard deviation, so it's going to be equal to standard deviation divided by the square root of the sample size, which is 40, Hit enter, and my standard error is basically 1. Okay, and now I'm going to calculate my confidence interval. Okay, my confidence interval is going to be equal to, I'm going to do something now that makes a big assumption. I'm going to say it's equal to 42 minus 1.96 times the standard error. And it's going to be equal to 42 plus 1.96 times my standard error. Oops, I made a mistake there. Try this again. Equals 1.96 times 42 plus 1.96 times my standard error. Enter. 40. It's between 40 and 44. I'm 95% certain it's there. The only problem is I'm not really 95% certain because it's a relatively small sample size. We're going to get into this in a little while. Technically, anything, most statisticians will assume anything over about 30 people, a sample of size 30, is kind of a pretty good approximation of the population standard deviation. And they consider a large sample, and they will just use 1.96 because the difference that you would need to make it a little bit wider to make up for your extra error that you have is really not significant enough to bother with. Okay. However, let's say that this were even a smaller sample size. Let's say the sample size were, for argument's sake, the sample size were 10. The sample size of 10. Okay, that's my standard error. Now, all of a sudden, my confidence interval is a lot wider, okay, because my standard error is different because the sample size is smaller. And but I'm still multiplying by 1.96. A sample size of 10 gives you a really poor approximation of the standard deviation, okay, for the population. So I really, at this point, I really can't just depend on that 1.96. Well, what am I going to do to deal with that? I'm gonna just pull up something here I can draw with. Okay, guys, I'm trying to pay attention to you. Wider, yeah, I'm okay. Let me get a pen here. Okay, so when I'm looking at my samples, my repeated samples, if I have a very large sample size, n equals 1,000, or if I know the population standard deviation, I have any sample size basically, right? I know how those samples are going to be distributed. If I repeat, because really, whether they fall on this side of the population mean or on this side of the population mean, how far away from the population mean they fall, well, that's all going to be taken into account by what the standard deviation is equal to. In other words, if the standard deviation is a large number, they're going to be spread out more. right? But it will always be 95% is going to be 1.96 standard deviations below the mean to 1.96 standard deviations above the mean. Problem I have now is if I don't know that, well, now I have a bit of extra uncertainty here. If my sample size is big, like n is equal to 1,000, well, my calculation for my standard deviation really gets pretty close to what the population standard deviation is. So pretty much the distribution I would expect from that sample size, if I repeatedly took samples of size 1,000, I'd expect it to be pretty much the same one that I would get for the z-table, right? 1.96, 1.96 represents 95% of the population. Now, as that sample size gets smaller,
It's 8 o'clock.
thank you. If that sample size gets smaller, what happens is that I can't be as certain. So this distribution starts to get wider. In other words, in order to be sure that I have 95% of the population, I might have to go out to 2.1, plus or minus 2.1 standard deviations. And if the sample size is really small, like 10, I might have to go out to say 2.5, minus 2.5 standard deviations, and plus 2.5 standard deviations. What does that mean? That means when I calculate my confidence interval, X bar, it's plus or minus, instead of 1.96 for a sample size of 10, I'm just going to make up a number. It may be 2.5 times the standard error. You calculate standard error the same way, but you make up for the inaccuracy because of your sample size by increasing the size of that 2.5. How do I know how much to increase it by? Anybody reading ahead or studying ahead? How do I find what that number should be? Instead of calling that a z-score, I'm going to give that a new name. I'm going to call it a t-score. Anybody looked at the t-tables yet? Does that come up? Okay, there's one on Blackboard that I put up for you. Okay, you guys at home, if you want, you can get it from Blackboard. Okay, let me see if I can get it here. Okay, there's a Z. Oh, first of all, number one, Z, you remember the Z tables? We got those, right? No problem. Okay, here's a T table. This is from Agresti. Here's a T table. Let me size this up a bit. Okay, let's look at this T table. First of all, we got a problem when we use the T-scores. And that problem is, I just mentioned that we got one distribution curve for one size sample and another one that's wider for a smaller sample. In other words, every sample has its own distribution, has its own z-table, except that it's a t-table. So you could do this one of two ways, or one of three ways. You could calculate the t-score on Excel or on a calculator of some kind that does this kind of stuff, or you could have a z-table for every sample size ever, right? Pretty inconvenient. Or you can have a single table that only gives you the t-score that you need for the stuff you use frequently. In other words, we're always interested in 95% or 90% certainty or 99% certainty. Why not just make up a table that'll give you that value of t? You know what that range would have to be in standard errors for you to capture 95% of the samples or the mean. Okay, so first thing I have is I have the sample size here in this column, except they don't call it the sample size, they call it DF. Any opinions what that means? Degrees of freedom. Degrees of freedom is the sample size minus 1. Okay, just to give you a rough idea, if you have a sample size of 1, you only have that value. You have no other value you can choose from. You don't have any degrees of freedom. If you have a sample size of 2, you have 1 degree of freedom. You can choose one or the other, and so on and so forth. So it's a sample size minus 1. So our sample size in this case, I mentioned in the second part of this, was 10. So if I have a sample size of 10, I have 9 degrees of freedom. If I want a 95% confidence interval, what should I use instead of 1.96? I should use 2.26 for my confidence interval. I got a question back there. Yes.
So what is the cutoff number? Like, you listed the 30?
Most of the time it's 30. I'm going to give you an example of that. The question was, what's the cutoff number for using the t-table instead of using 1.96? In most cases, it's going to be 30, but I'm going to show you how this works. If you look at this, if a sample size is 20, right, I go to 20, okay, keep in mind the column that's the 95% confidence interval is this one right here, the third one over. It's going to scroll out of the picture. If the sample size is 20, it would be 19 degrees of freedom, we'd be using 2.09. If the sample size is 25, we'd be using 2.06. If the sample size is 30, we'd be using 2.04. Notice that we're getting closer and closer to 1.96. We don't get to 1.96 until the sample size is infinite. Because what is an infinite sample size? It's the entire population, right? That's sigma. We would know what sigma is. That's when you get to 1.96. But on a practical basis, when we're this close, in other words, a lot of times you hear me say, well, I'm going to use 2 for the standard error because it makes the calculation convenient. Well, a lot of times statisticians will use a sample size of 30 as a large enough sample to just not bother with the t-table and just use the z-scores. So now, if I really,
Is that the degrees of freedom on the left, not the sample size?
that's the degrees of freedom. Yes.
31.
So for 30, it would be 31. Exactly. Yes.
If I can add
It would be actually for 30, it would be 29. Yes.
if I can add something, when you use software to do this kind of a test, it's just going to use the t table. Because if you're estimating the variance of the standard deviation from the sample, t is correct. It's just that it starts getting closer and closer to t as you get to a large sample. But if you're estimating from the sample, you don't go wrong with t.
Just to repeat that for you guys at home, Professor Waldron pointed out that if you are using software such as SPSS, SPSS will always use the t-score because it's got an infinite t-table built into it. So we can calculate any t-score it needs. So, and since it's a machine, it's not any extra work for it. So it will always use the exact t-score. For you guys, once you get over 30, in most cases, you're going to be probably be permissible for you to use the z-score. So I'm going to go back to the problem we were just looking at. And for a sample size of 20, we might have considered using 2.02 instead of, if I can get back to it, Excel. Oops, wrong one. Oops, nope, I still got the wrong one. Where'd I put it? There it is. It's back here. So I might have considered using, if I wanted to be more precise, 2.02 instead of 1.96. Okay, not much of a difference there, is there? So that's why 1.96 probably would not be a terrible assumption to make in a situation where I have a sample size of 40. Okay, so that's our first look at the t-score and at the t-table. And what the t-table is, t-score and t-table are doing for us is it's making up for that extra error. Remember that our formula for finding the standard error was sigma, the population standard deviation, over the square root of n. Since we don't know sigma and we're using estimated standard deviation, in other words, a sample standard deviation, we introduce that extra error, so the t-score is making up for that extra error for us. So we're going to be using t-score since we, in real life, we're almost always dealing only with samples and not with populations, then we're almost always going to be making accommodations like that. Okay, unless the sample size is very large, and we're going to make the assumption that the standard deviation we calculate from the sample is basically the same as it is for the population. Okay, let's move on to the next problem.